Hi everyone, this is K Devender Reddy, Assistant Professor in Department of Electrical and Electronics Engineering. And today in this video, we are going to discuss about phasor diagrams of alternator under different loading conditions. Before into the phasor diagram under different loading conditions, let us look into the effect of armature reaction on the induced EMF of the alternator. And we know the armature reaction having three effects. One is cross magnetization effect. Second one is the demagnetization effect. Third one is the magnetizing effect. So the flux produced by the armature will distort main flux will distort the main flux. It either distortion or it may be of demagnetizing or it may be of magnetizing. Either it can weaken the flux, either it can weaken the main flux or it can be strengthen the main flux, that is depending upon the load connected to the alternator. Under unity power factor loading conditions, the armature reaction effect is partly distortion and partly demagnetizing. Where in the case of the lagging power factor loading condition, armature reaction is demagnetizing, and leading power factor loading condition, armature reaction is magnetization effect. And we already known about leakage flux. The flux which will not complete its path is called as a leakage flux. The leakage flux produces a self-induced EMF in the armature conductors. So drop due to the self-induced EMF, that is called a leakage flux, we can naming as leakage reactance XL. So in addition to the winding resistance, in addition to the armature winding resistance, we have another term called leakage reactance, that becomes the winding is more inductive in nature. So the armature winding, which will be having in addition to the resistance, we have one more term called leakage reactance XL. And also the effect of armature reaction also represented in terms of a fictitious reactance called XA, armature reactance XA. Now the synchronous impedance of the alternator, which is equal to RA plus J times of XL plus XA, drop due to leakage reactance, drop due to synchronous armature reaction effect. Combined these effects we can naming as RA plus J times of XS, which is equal to synchronous impedance of the alternator in terms of the ohms. So all these leakage reactance as well as the armature reaction will affect your induced EMF of the alternator. That will be look into the this video, how the type of the load will affect your induced EMF, and how we'll draw the phasor diagram for induced EMF or per phase quantity of induced EMF of the alternator. For first example is unity power factor loading condition. That is, I am taken as voltage as a reference vector, that is represented with the V phase. Under unity power factor loading condition, current is a in phase vector for V voltage. So that is represented by red color line here, IA. Drop due to winding resistance, that is IARE, that is along the phase of V phase, and IA because it is a resistive load and current is co-phasor with a V phase, obviously your winding drop, resistance drop also co-phasor with IA. Drop due to leakage reactance, it is of a perpendicular one, that is J, that is 90 degree here. Next, drop due to the impedance triangle, that is a drop due to synchronous reactance of the alternator is equal to drop due to synchronous impedance of the alternator is equal to IARA drop plus J times of IAXS drop. And next one, the induced EMF of the alternator. Induced EMF of the alternator is equal to E phase. Now we can write here from triangle OBC, right, from a triangle OBC, OC square is equal to OB square plus BC square. OB is nothing but OA plus AB, OA plus AB whole square plus BC square is equal to OC square. And OC square is nothing but E phase square from the phasor diagram, which is equal to OA, that is V phase, plus AB drop due to winding resistance, IARE whole square, plus BC square, that is IAXS whole square. So E phase is equal to square root of V phase cos phi plus IARA whole square plus IAXS whole square. This is the expression for induced EMF per phase quantity when the alternator is unity power factor loaded. Similarly, you can also mention the vector diagram in another way, that is by splitting the synchronous reactance effect, synchronous reactance drop, splitting into armature reaction effect, armature reaction reactance drop, as well as the leakage reactance drop. That here in this diagram, in this vector diagram, I clearly shown the drop due to leakage reactance is IAXL, and this is a drop due to armature reaction effect, that is IXA. So here the induced EMF E and E naught. The E naught represents the maximum no load induced EMF. Maximum no load induced EMF. E is the induced EMF of the alternator across the terminals after overcoming the armature reaction effect. So this E is always less than E naught because of the armature reaction effect of the alternator. Similarly, when alternator is loaded with unity power factor, when alternator is loaded with lagging power factor loading condition. Similarly, take it as V phase as a reference vector, and let us take it as the IA armature current as a reference vector, or you can also take it as a V phase as a reference vector. Under lagging power factor loading conditions, voltage leads the current by certain phase angle phi. If it is exactly absolute zero lagging power factor, the phase angle between a voltage and current, obviously it is 90 degree. But I am not confining it is a zero lagging power factor. It may be of more than that. That is why I am not mentioning the phase angle between voltage and current not 90 degree. So here the voltage V phase is a leading vector and the current is a lagging vector with an angle called phi here, phase angle between voltage and current. Next, drop due to armature resistance, which is a co-phasor for current, IARE, and you can also draw that vector here. Let us I am naming it as a letter D, OABC, D, let it be E. For example, ED vector is equal to AB vector, which represents the same quantity IARA, and a drop due to synchronous reactance will be DC vector, that is IAXS. Now, the induced EMF E phase is equal to E phase vector is equal to V phase vector plus drop due to armature resistance, that is IARA, plus drop due to synchronous reactance IAXS vector. Sum of these three vectors is equal to induced EMF of the alternator under lagging power factor loading condition. You can derive the expression for that by considering delta OBC first of all, delta OBC, and OC square is equal to OB square plus BC square. OB is nothing but OA plus AB. OC square is equal to E phase. E phase square is equal to OB is equal to OA plus AB whole square, and BC is equal to BC and BD plus DC whole square. and E phase square is equal to OA is V phase cos phi plus EB IARA whole square plus BD V phase sin phi plus DC IA XS whole square, and if it is a E phase it is equal to square root. E phase is equal to V phase cos phi plus IARA whole square plus V phase sin phi plus IA XS whole square root volts. This is the voltage induced EMF induced in the alternator under lagging power factor loading conditions. So similarly, you can also express by splitting the XS drop into XL as well as the XA. That is a similar phasor diagram. And you can also express the alternator induced EMF for the alternator under leading power factor loading condition. Here I am showing that V phase as a reference vector and current I is a leading vector because it is a capacitive load, that is a leading power factor loading condition. Current always leads the voltage by a power angle called a phi. Next, IARA drop, which is of a parallel to the IA. IARA drop should be a parallel to the I. So from V I am drawing a parallel line for IA that is represents the IARA drop. Then IAXL drop, this will be drop due to leakage reactance. This will be drop due to synchronous armature reaction reactance. So the similar way like before lagging power factor loading condition, V phase can be calculated, that is V phase cos phi plus IARA whole square plus V phase sin phi minus IAXS whole square root. So this is the expression for induced EMF of the alternator under leading power factor condition. So you can take it as plus or minus, plus sign for lagging power factor, plus sign for lagging power factor loads, and minus sign for leading power factor loading conditions. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.